going to go ahead and get started. Right, and we're going to go right back into an ice problem, and this is a harder one mathematically. All right, so let's go ahead and work on this. So consider the following at 345 degrees C. And what we're going to do is we're going to calculate the equilibrium partial pressures, and I'm going to use PP, of COCl2 gas, CO gas, and Cl2 gas if the initial pressure of COCl2 gas is 0.351 atmospheres, and Kp is equal to 0.465. Okay. And our equation, oops, almost forgot this, COCl2 gas is in equilibrium with CO gas plus Cl2 gas. So here's my equation. In other words, what we're doing here initially is we're opening the flask, we're putting a bunch of COCl2 in there so it'll have a pressure of 0.351 atmospheres. Put the top back on, and we want to see what happens to this equilibrium over time. All right, well, let's make our ice table. And let's go ahead and fill in what we know. Okay, so we know that we're starting with 0.351 atmospheres here. All right, we don't have any of this, and we don't have any of this. All right, so now we know that this is going to go this way. So we know that this is going to go up, this is going to go up, this is going to go down. All right, so our change, this is going to go up by x times 1. All right, so this is going to go up by x. This is also going to go up by x. This is going to go down by x. Right, so now to get this change, we just add this all up. So we end up with 0.351 minus x. This is just plus x, and this is just plus x. Okay. All right, so now we have this. This is our variables. Right, let's go ahead and write our equilibrium expression. So we know that Kp is equal to the pressure of CO times the pressure of Cl2 all over the pressure of COCl2. Okay, now we can substitute into this formula. All right, we know Kp. All right, we know these guys with these variables. So let's go ahead and substitute. So we have 0.465 equal to positive x times positive x all over 0.351 minus x. All right, so when we do some math here, we have 0.465 equals to x squared all over 0.351 minus x. Okay, all right, well, let's get this over here. All right, so we can get x squared by itself. All right, so we're going to have to distribute. So we get x squared equal to 0.0163 minus 0.465x. All right, let's get this over here. So we have x squared plus 0.0163 0.465x minus 0.0163 equals 0. Yeah, now what are we going to do with that thing? Well, how do we solve it? Correct. We need to use the quadratic formula. Okay, doesn't that sound fun? Oh, it is. All right. So our quadratic formula, right? X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. All right, so now for those of you that don't know here, all right, a A is equal to 1, B is equal to 0.0, hold on. Okay, I figured out my math issues. All right, I got math issues. So what I want to do, all right, is I want to, let's start after this again. All right, so let's do it over here. All right, so when we cross multiply this, we should get x squared equal to 0.163 minus 0.465x. Right, now we want to get all of that on the same side, so we get x squared plus 0.465x minus 0.63, and that equals 0. All right, now this is what we have to put into our quadratic. All right, so our quadratic is this thing. All right, and our a is going to equal 1, our b equals 0.465, and our c is negative I'm giving you guys a hard time, negative 0.163. All right, so now we're going to put that into the quadratic. All right, so our quadratic is x equals negative b plus or minus the square root b squared minus 4ac all over 2a. All right, we're going to substitute in here. So x is going to equal negative 0.465 plus or minus the square root of 0.465 squared minus 4 times 1 times negative 0.163 all over 2 times 1. Okay, so if we keep going with math, x equals negative 0.465 plus or minus the square root of 0.216 plus 0.652. That's all over 2. When I do this math, we end up with negative 0.465 plus or minus 0.932 all over 2. Okay, now when we do this math, right, we'll do the, okay, you gotta do it once for the positive and once for the negative. Right, so if we do it for the positive first, we end up with x equaling 0.234 atmospheres. And if we do it for the negative, we get a negative 0.699 atmospheres. Right, now, we can't have a negative pressure. So we're going to reject this one. So this has to be our answer. This must be x. Okay. Now that we know x, we can go up here and we can go back and fill in our pressures. All right, so if we go back here and we do 0.365 minus our x, okay, we end up with 0.117 atmospheres, 0.234 atmospheres, and 0.234 atmospheres. And this would be our equilibrium pressures. Wow, I know I messed up the math on you guys. All right, hopefully you were able to follow what I did. All right. This is a pain in the butt. I get it. All right. In reality, I don't think you're ever going to have to do this because I'm going to give you a shortcut. All right, I'm going to give you a shortcut with these that most of the time you're going to be able to use. Not always, but most of the time. All right. In reality, do I think you'll get one of these on the final exam, or would I give you one of these where you have to use the quadratic? I can't imagine that they would ever do that to you, all right? But is it possible? Yes, all right? But in reality, I don't think they will, all right? So now, let me show you a way that we can estimate this when you have this issue where you run into this quadratic issue. And this is going to be important actually in acids and bases, all right? So let's simplify it a little bit. So sometimes we can get away with estimating. If our Kc or Kp is very large or small, okay, if this is true, okay, hey, just to remind you, if K is greater than what does that mean? K is greater than 1, that means we favor products. It's going to go towards my products. If K is less than 1, okay, it favors my reactants. Okay, it favors my reactants. Right? Okay, so number 1, if the initial concentration of reactants are given with a very small Kc, we can assume these concentrations will not change when equilibrium is reached. Okay, so if we have some equation and my Kc is really small, right? It favors the reactant side. And if it's really small, really basically what that's saying is that none of the reactant is going to come to be product. Now, is a little bit? Yes, a small amount is going to go over there, but it's insignificant. It's not going to make much product, okay? At the same time, we can say this. if the initial concentration of product are given with a large Kc, we may assume the concentration of the products will not change. When equilibrium is reached. All right, so in this case, we have all this product, all right, and it favors the product so much that very little of the reactant's going to be made. All right, so we can use these two ideas. All right, so let's try something with it. And do I have enough space? I don't have enough space, so I'm going to go ahead and go on to the next page. So let's say I have this equation. 2SO3 gas in equilibrium with 2SO2 gas plus O2 gas. Kc for this reaction is 2.4 times 10 to the minus 25th. Okay. It's an extremely small Kc. So if we look at this, all right, at equilibrium, there's going to be very, very little of this, but lots and lots and lots and lots and lots of this. Okay, so very little SO3 I think I messed that up. I need to wake up. Very little SO3 will react to produce products. So if our K is less than 1, it favors our reactants. All right, so this is way, 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 way less than 1. Okay, so that means it's going to favor this. So almost none of this will react to produce any of this. So the concentration of this really isn't going to change. Okay. All right, so now let's say that we have 2.00 moles of SO3 placed in a 1.00 liter flask. We want to calculate the concentrations of all three at equilibrium. All right, so this again is an ice problem. So we have 2 SO3 in equilibrium with 2 SO2 plus O2. Let's go ahead and make our chart. Initial change equilibrium answer. Okay, so now first of all, this is in moles. We got to convert it to molarity. It's moles per liter, so we got 2 divided by 1, so our molarity is still 2.00 molar. So we're starting with this, and we have none of this to start with. Okay, so that means this side's going to go up, this side's going to go down. So now this is going to go down by x times 2. This is going to go up by x times 2, and this is going to go up by x. All right, so now if we add these up, we get 2.00 minus 2x plus 2x and plus x. Okay, now if we write our equilibrium expression, Kc is equal to the concentration of SO2 squared times the concentration of O2 divided by the concentration of SO3 squared. All right, let's go ahead and substitute. So we end up with SO2, so it's 2x, so we got 2x squared times x all over 2.00 minus 2x squared. Now, we are heading for a quadratic equation problem, all right, and that's, we really don't want to go there, all right? So we can make this assumption though, okay, we know that this right here is basically not going to change, all right? So really what we're saying is that this change is extremely, 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 extremely small. So if this is extremely, 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 extremely small, is it going to change this initial concentration very much? The answer is no. Yes, it does, but it's going to be extremely small. So we can assume that 2x is very small. Okay, it's very small. It's insignificant. All right. So if we take 2.00 minus 2x, and this is extremely small and it doesn't matter, we're just going to assume that the answer to this is going to be 2.00. All right. So instead of using 2.00 equals 2x squared, we're going to use 2x squared over x divided by 2.00 squared. Okay. And our Kc, we know, is 2.4 times 10 to the minus 25th. This makes our life way, way, way easier. Okay. So now, when we do some math, okay, we end up with, do I just want to, this times this is 2x cubed. All right, let's multiply these together. So that's 4 times that. So we end up with 2x cubed equals 9.6 times 10 to the minus 25th. X cubed equals 4.8 times 10 to the minus 25th. So we take the cube root of both sides. X equals 8.0 times 10 to the minus 9th. Okay. All right, so this is my X in here. So let's go ahead and fill this back out. We just said that this is basically what? Okay, it's basically no change, and we assumed that this was 2.00 molar. All right, when we place x in here, turns out that so we're going to multiply x by 2, we get 1.6 times 10 to the minus 8th moles, right, which is extremely small, which is what we predicted. All right, and then we have to look at this guy right here, and this is 8.0 times 10 to the minus 9th, right, molar, which again is extremely small. Now, when we make this assumption, okay, when we make an assumption like this, so you want to go ahead and you want to look, okay, we want to look at it, make sure our assumption is correct, right? So we want to make sure x is reasonable. Okay. So we assumed that 2.00 minus 2x was basically 2.00. is that the case? So let's put in what we found for x. So if we go 2.00 minus 2 times 8.0 times 10 to the minus 9th, we get 1.999, 1, 2, 3, 4, 5, 6, I think 7 nines, 1, 2, 3, 4, whatever. All right, with sig figs, this is going to equal 2.00. All right, so this is telling me that my assumption is pretty good. All right. Okay, so this is telling my assumption's pretty good. All right. You do want to check it, because if you get some number that's not near your assumption, there's an issue somewhere. All right, so this works out pretty well. All right, so these are my concentrations. All right, we're gonna do this a lot in acids and bases. All right, and you'll see why. Whew. All right. We're going to talk about solubility, and I think that's where we're going to stop today. Okay, so let's talk about solubility product. And this is called KSP, equilibrium constant of the solubility product. So we're talking about things dissolving. All right, so this is used in the solubility of slightly soluble compounds. The equilibrium expression always represents the product of the ions produced when the compound dissolves. Now, let's talk a little bit about slightly soluble. Okay, I know we've talked about solubility already. All right, and we said like dissolves like, so polar dissolves polar, nonpolar dissolves nonpolar. All right, but in reality, that's not completely true. So for example, carbon dioxide gas will dissolve in water. This is very nonpolar. This is polar. Okay. CO2 will dissolve in H2O. Not very much of it will. Okay. It's going to be a very, 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 very small amount. Okay. But a little bit of it will dissolve in water. So we say that CO2 is slightly soluble. All right. And that's kind of what we're going to be dealing with in these problems. Okay, now, it is generally accepted that if at least 0.1 moles of a salt will dissolve in 1 liter of water. Okay, so it makes a 0.1 molar solution. Okay, if we can get this, it is soluble. So if 0.1 moles will dissolve in a liter, we say that it's soluble. Okay, anything less than that is going to be slightly soluble or maybe even insoluble. So saturated solutions of insoluble salts have concentrations less than 0.1 molar. But they do dissolve to a very small extent. And these end up being just equilibrium problems. Okay, so let's go ahead and look at one. Okay, let's say we have FeOH3 solid in equilibrium with Fe plus 3 aqueous and 3 OH minus aqueous. The KSP for this is equal to 1.6 times 10 to the minus 39th. Okay, so what is that telling me? Holy crap. Sorry. Okay, what this is really telling me is that this is not going to go over here. In other words, it is not going to dissolve into this. It doesn't want to. All right. Now, will a tiny bit of it dissolve? Yes. All right. But, okay. This is a solid. Okay. This solid is not going to dissolve into water very much. All right. Now, let's write my equilibrium expression. KSP is equal to the concentration of these guys times the concentration of OH minus cubed. But this is not in the equilibrium expression. Why? Because it's a solid. All right, remember, all right, solids and pure liquids are not included in your equilibrium expression. So FeOH3 is a solid. So it is not in the expression. Okay. All right. So now let's go ahead and calculate, all right, some equilibrium numbers. So let's rewrite our equation because this is an ice problem. FeOH3 solid is in equilibrium with Fe plus 3 aqueous plus 3 OH minus aqueous. Let's make my ice table. All right, so now, okay, we don't have a concentration here. This is just a solid. Okay, it doesn't have a concentration. All right, this we're starting with, so we're starting with water, and we're going to put this in here. So we're starting with this is 0. We have none of this in solution, and we want to know how much of this is going to go in. All right, well, we know that this is going to go down, so this is going to go down by x, which means this is going to go up by x, and this is going to go up by 3x. All right, so now, when we subtract x from the solid, a tiny bit of this solid is gonna dissolve, but basically what's left at equilibrium is we have a whole bunch of solid. Okay, that's okay. Over here, we're going to have plus x, and this is plus 3x. All right, well, let's substitute into my equilibrium expression. KSP equals the concentration of Fe plus 3 times the concentration of OH minus cubed. Our KSP is 1.6 times 10 to the minus 39th equals x times 3x cubed. Okay. Now, when we do this math, x ends up equaling 8.8 times 10 to the minus 11th molar. Okay. So here, the concentration of this would be 8.8 times 10 to the minus 11th molar, and the concentration of this would be 2.6 times 10 to the minus 10th molar. All right, now, this is very, 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 very small amounts that are dissolving. All right, so this number that we calculate, okay, x, has also got another name. Okay, this is the solubility. This is considered the solubility product of FeOH3. So the solubility product, or the solubility of FeOH3 is 8.8 times 10 to the minus 11th moles per liter. Okay, so I think we should probably push on and talk about common ion effect. Again, this is really similar to what we just did. So I think we should probably go ahead and do this. So let's talk about what's called the common ion effect. And what this is a decrease in the solubility of a compound when it is dissolved in a solution that already contains an ion in common with the salt being dissolved. Okay, and to show you this, we're going to go back and we're going to actually work with what we just did with iron hydroxide. All right. So we're going to be working with FeOH3 solid in equilibrium with Fe plus 3 aqueous plus 3 OH minus aqueous. Now what this is saying is we're going to dissolve this into a solution. All right. But what we're saying is, look at, we're going to put this in a solution that already has some iron in it. So maybe there's some iron chloride already in the solution before we put this in. Right? If there's iron already in there, it's going to affect how much of this will dissolve. So it would have a common ion, and it's called the common ion effect. All right, so let's say there is 6.5 times 10 to the minus fifth molar solution of Fe plus 3 ions in the flask. So we dissolved iron chloride or something, and we have and in the flask to start with, there's a concentration of 6.5 times 10 to the minus fifth molar of Fe plus 3. All right, remember our KSP was equal to 1.6 times 10 to the minus 39th of FeOH3. So very, very little dissolves. Let's make an ice table. Okay. So again, we're going to dissolve this. So this is just a solid. This time we are starting with some of this. We have 6.5 times 10 to the minus fifth molar solution, and we have none of this. All right, we know that some of this is going to dissolve. We'll say X will dissolve, so we'll have some solid still left. Okay, which means this is going to go up by X. This is going to go up by 3X. None of that is new. All right, so if we come down here, we get 6.5 times 10 to the minus fifth plus X and plus 3X. Okay, now, X is going to be extremely, 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 extremely small. Okay, very little, very tiny, 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 very small amount of X is going to be produced. So small that it's insignificant again. All right, it's insignificant. So if we add an insignificant amount to this, all right, is it really going to change this? Well, so since X is going to be so much smaller, I mean so much smaller than 6.5 times 10 to the minus fifth, really what I can say is this is really just going to equal 6.5 times 10 to the minus fifth. Okay. I hope everyone understands that. Okay, so now if we go into KSP equals the concentration of Fe plus 3 times the concentration of OH minus 1 cubed, we have 1.6 times 10 to the minus 39th equal to, and instead of this, we're just going to write 6.5 times 10 to the minus fifth times 3x, and that's cubed. Right, when we do this math, now we have x equal to 9.7 times 10 to the minus 13th molar. Okay. So now, okay, that's how much of this iron will dissolve over here. All right. Extremely, 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 extremely small amount. All right. So now we multiply this by 3, and we would get 2.9 times 10 to the minus 12th molar of this. Okay. So an extremely small. Now this is my new solubility product for this equation. Okay. On the first page, we calculated it to be 8.8 times 10 to the minus 11th. Now it's 9.7 times 10 to the minus 13th is all molar. Okay, we can dissolve much, 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 much less of this because that iron's in there. Okay. So we can dissolve much less iron hydroxide because the solution already had iron in it. Okay, this is called the common ion effect. All right, so let's try this question. The molar solubility of MgF2 is determined to be 1.18 times 10 to minus third moles per liter. Calculate KSP. Okay, so this is a little bit different problem. So we have MgF2 solid in equilibrium with Mg plus 2 aqueous plus 2F minus aqueous. All right. Let's make a nice table. All right, so this is Fe. MgF2 is a solid, so X will dissolve, so this will be minus X will dissolve. We have none of this to start with, so this one's going to go up by X, and this is going to go up by 2X. So we got plus X plus 2X. Okay. Now, KSP is equal to the concentration of Mg plus 2 times the concentration of F minus squared. Well, it gives us the molar solubility. Okay, it gives us this. So it's actually telling me how much Mg plus 2 is going to be produced. Okay, so this number right here is the amount of Mg plus 2 produced. Okay, so this is going to be 1.18 times 10 to the minus third molar. This is the molar solubility, right, or the solubility product. Okay, so now that I know X, now I can figure out this guy because I can multiply it by 2. So this ends up being 2.36 times 10 to the minus 3 molar. Now that I know these two numbers, I can calculate KSP. All right, so I just substitute in KSP equals 1.18 times 10 to the minus third molar times 2.36 times 10 to the minus third molar. That's squared. So our KSP is 6.57 times 10 to the minus 9th. Okay. All right, this is just a little bit different problem. All right, I figured I'd quick show it to you. All right, we're going to stop here for today. Make sure you look at the posting, and we will move on. All right, have a great afternoon.